This is a circuit description of the Tektronix 7904 oscilloscope. The instrument is a mainframe only, requiring vertical and time-based plug-ins to make it work. The scope has a band pass of 500 megahertz, and with appropriate time-based plug-in units can provide 500 picoseconds per division delaying sweep. It features a full 8 by 10 centimeter CRT with 24 kV accelerating potential, providing extremely high writing rate. The scope has knob readout and display switching that provides vertical switching between left and right vertical plug-ins, as well as switching between channels of a dual trace plug-in. Horizontal display switching provides simultaneous viewing of two time bases at either independent sweep speeds or in delaying sweep mode. The use of one single time base and a dual time base allows 3 displays in delayed mode. Knob readout and display switching logic will not be covered in this tape. We will discuss trigger selection, however. For information on knob readout, I refer you to the tape entitled 7000 Series Knob Readout Circuit Description, and for switching logic, the tape entitled 7000 Series Display Switching. We'll use the 7904 service manual for reference. We'll assume that you know how to operate the scope and its plug-ins, and that you have an understanding of the basic Tech Scope circuit concepts covered in the series of Tektronix circuit concept books. Now we'll begin with pull-out schematic 6, the vertical amplifier. CRT deflection sensitivity is 4.5 volts per division, push-pull. You may want to make a note of that. Center screen voltage is 34.5 volts. Then over at the left, the inputs are from the left and right vertical plug-ins. The standard 7000 series interface signal values of 50 millivolts per division push-pull are used. Now that's 25 millivolts per division per side, of course. Now the input lines are terminated in 50 ohms, so the input current is 0.5 mils per division. Voltage gain for the entire amplifier is 90. U625 is the vertical channel switch. It's a new IC designed for this faster vertical. It responds to the usual left-right commands, as well as add and the off command. Now the off command is used during the time that the readout characters are being written. The Y portion of the readout signal comes in at the center of the page where it says Y readout. Trace separation information feeds into the same amplifier just below. Now notice just below that the vertical off command comes in, which disconnects the trace separation during the time that the readout characters are being written. Now that entire output goes into U685. Also into there is the output from the channel switch. Now U685 is an M77A IC. It's an FT doubler, and in this case has a gain of about 5. Okay, its output drives push-pull into the output IC, U745. Now that's a hybrid design, including an IC FT doubler, followed by a discrete push-pull output amplifier. And its output in turn drives a CRT. Well, let's go back to the input and look at the vertical channel switch in more detail. U625 is a Tech-made IC, MO71. It was designed especially for this instrument. It uses 4 gigahertz transistors and has a rise time of 175 picoseconds, and in the configuration shown here has a gain of 2. Now pins 6 and 7 are in parallel inside of the IC, as are pins 8 and 9, and so on down the line. Now the lead inductance in at pin 7 and in at pin 6 forms a T-coil, and C603 appears across the T-coil. The entire amplifier maintains a 50 ohm environment, and that's true here where R603 in parallel with selected resistor R602 provides the 50 ohm environment. Now the selected resistors are necessary because of the differing betas on the input transistors would provide a shunt resistance which would differ one transistor to the other, so the selected resistors take care of that variation. As I said earlier, the signal current is 0.5 mils per division per line. Now the emitter connections for the input stage are found down below. Notice that they're labeled left and right and so on. The pluses and minuses are turned around, however. Pins 4 and 5 are for the plus input and relate to inputs pins 6 and 7. Now inside of the IC are 21.8 ohm nichrome resistors between pins 4 and 5, 10, 11, 16, 17, and so on. And they are shunted by selected resistors, which match that to 18.5 ohms or so, but that's not the important point. Now what we do need to match are the gains of the left and right input amplifiers. You see, so that we have adequate common mode rejection when we invert one and go to added mode. Then match the overall gain of the amplifier. Well, since those nichrome resistors are 10% devices, and since the beta of the transistors inside of the IC will vary with ICs, and you can see the need for selected resistors in this configuration. Now the RC time constants right across the selected resistors are rather long time constants, and the purpose is to provide thermal balance for the transistor amplifiers within the IC. Now each emitter line draws about 21 mils, about 1 mil of which is used up in the beta of the transistors inside of the IC, so that coming out at pins 1 and pins 2 we have 80 mils of standing current per side. Now right between pins 1 and 2 inside of the IC is a tapped 100 ohm resistor, or I guess we should say two 50 ohm resistors to provide the 50 ohm source impedance to reverse terminate the delay line. Now again, those are nichrome resistors and 10% devices, and deliberately cut a little bit large so that R646, another selected resistor, maintains that 50 ohm source impedance we need to reverse terminate the delay line. Well, we haven't talked about the control lines. First, pin 14, which is the vertical mode command. Now if that line is high, then the right input is passed. If it's low, then the left input is passed. Now if pin 15 is high and pin 14 is low, then we add left and right, and that combination is taken care of by the switching logic. Then the vertical off command in at pin 12 goes high when we want to turn off this vertical input amplifier while the characters are being generated in the knob readout. Now in this IC, whenever an amplifier is turned off, the current is shunted in another direction, and that's true in the off command. Now when pin 12 is high and the amplifiers are turned off, the full current flows through the tap between those two 50 ohm resistors that I mentioned, between pins 1 and 2, and we get a little voltage drop across those 50 ohm resistors, dropping the collector of some transistors inside of the IC to the point that they'll saturate. Well, there's a recovery problem, of course, when that happens. So up above, there at pin 3, we have a voltage setting emitter follower, Q617, that supplies about 2.8 volts. Now that goes to the bases of those transistors that we said would saturate. Now, just as soon as we want the vertical off command to switch the current inside of this IC and turn off the input amplifier, then we get the high in at the base of Q616, turns that transistor on and saturates it. Its collector comes down and drops the emitter of Q617 to about 1.1 volts. Well, that drops the basis of those two transistors down to the point that they will no longer saturate. Well, as I said earlier, this amplifier has a gain of 2, so the level going into the delay line is 50 millivolts per division per side. The delay line is a 66 nanosecond line. We've covered the reverse termination. Now the output termination is 50 ohms as well. Now we have two 50 ohm compensating networks, or compensating networks that maintain a 50 ohm environment. One of them composed of L660, R660, R662, and the capacitors across it. Now that's 50 ohms provided it's loaded with 50 ohms. Now the next stage, composed of R667, part of L667, and R670 and C670, and that's 50 ohms provided it's loaded in 50 ohms. So let's start at pins 9 and 10 of U685. Now they're tied together, and a T-coil is composed of L676 and the lead inductance looking into pin 10, the conventional shunt across it, C675, and then pin 9 has the 51.1 ohm resistor, R677 to AC ground. Now that resistor is a bit inductive at high frequencies, so the network C676 and R676 compensates for that. All right, so at pin 10, essentially, we have 51.1 ohms. Now, if we go to the left of R670 and look to the right, we find that we have precisely 50 ohms. In other words, we have the 51.1 in series with R670 in parallel with R667, which comes out to 50 ohms. So far we've maintained the 50 ohm environment. And that network provides some high frequency compensation to compensate for delay line losses, dribble up and so on. Now that we have 50 ohms at the left of R670, we can play the same games with R662 in series with the 50 ohms in parallel with R660, and we come out with another 50 ohms to terminate the delay line. The RCL network provides some more high-frequency compensation for the delay line. Now, just to the left, we have an RCL network, R658, C658, and three inductors that are just lead length on the run, and that's called a boat rocker. Now, we've used that network before. Essentially, what it does is to compensate for a slight overshoot that occurs, an overshoot and a ringing. Well, if you draw that overshoot and the ringing following, it looks something like ocean waves. Well, this network irons out that overshoot and the ringing, suppresses the waves, and for some reason or other, they've come to call that a boat rocker. It's adjustable, as you'll notice. Now, this entire compensating network here has a signal loss of 40%, that is 60% of the signal passes. So U685 has a gain of 5 rather than the gain of 3 that one would expect to compensate for the loss in that network. Now the emitters are connected. They're at pins 5, 6, 12, and 11. Now pin 7 is the alternate base to input comparators, and the other bases there are at pins 9, 10, 3, and 4. So since pin 7 is at 6 volts, then that means that pins 3, 4, 9, and 10 are also at 6 volts. And the emitters, they're at pins 5, 6, 11, and 12 are one junction below that, so we can easily figure the standing current, and it's 30 mils per emitter. Now that's easy enough to see the currents in it, pins 5 and pin 11. Our pins 6 and 12, you'll notice, are tied down to the output of an amplifier, which provides the vertical portion of the knob readout information, and also what they've termed here Y-axis information. Actually, that's trace separation. Well, let's take the trace separation first. Goes into the base of Q694. That transistor and Q698 form a paraphase amplifier, which drives into a push-pull amplifier composed of Q710 and Q716, and that in turn drives the output amplifier Q723 and Q728. Now, each of the transistors in that output stage has 30 mils of standing current, and that, as you can see, goes into pins 6 and 12 of the IC up above and balances the 30 mils of standing current in it, pins 5 and 11. All right, let's go back and look a little more closely at the paraphase amplifier. You notice that its emitter tail goes off to the right there and down to R706. Now, we don't want trace separation at the time that the characters are being written, so you'll notice that the vertical off command comes in just a little below there. It lifts the base of Q705, which in turn lifts its emitter, and that in turn pulls up on the emitters of Q698 and Q694, turning those transistors off and removing the trace separation information. The emitter tail current now flows through Q705 and through the readout vertical centering adjustment up to the base of Q710 and makes up for the fact that the current was lost through the paraphase amplifier. Now that happens, remember, when we're writing a character, so that's a reasonable place to put the readout vertical center control, driving into the bases of push-pull amplifier Q710 and Q716. In the emitters of that push-pull amplifier stage is the vertical centering adjustment. Now Q710 and Q716 is in the circuit all the time, and we want vertical centering, of course, to be in the circuit at all times, and it balances the emitter connections up at IC pins 6 and 12. Now coming into the base of Q723 is the Y readout, as it's called, the vertical portion of the knob readout signal. So that means that Q723 and Q728 is a paraphase amplifier for that signal. So that's a current drive then into the emitters of the ICs there at pins 7 and 12. The line from the collectors of Q723, Q728 up into the IC is rather a long one and tends to be inductive. Now it's important that the emitters of that IC look into a purely resistive load. So the line from pin 6 and pin 12 looking down towards those 82 ohm resistors, although only 1.5 inches long or so, is a transmission line with a characteristic impedance of 82 ohms, terminated in 82 ohms, and then at the frequencies that we're talking about here, bypassed at the far end, that is the bottom of the 82 ohm resistors, by C685 and C689. Now those capacitors are low enough in value so that they don't interfere with the auxiliary Y information feeding up from the auxiliary Y amplifier. Now within the IC, between pins 5 and 6 and 11 and 12 are the 21.8 ohm nichrome resistors, and they're shunted by these selected resistors, again to control the gain of the amplifier. Now understand these ICs are coded so that in assembly, they know which value of selected resistor to use. Now, as I said earlier, this IC contains an FT doubler and has a gain of about 5. Now, the output transistor collectors are tied directly to pins 2 and 8, so any collector load is supplied externally. DC-wise, it would be the 51 ohm value of R735, and AC-wise would be that resistor in parallel with half of the network R731, L730, R730, and so on. Now, R730, as you can see, is the vertical gain adjust, varying the value of the collector load resistor. R731 is a thermistor with a positive temperature coefficient to compensate for a loss in gain at higher temperatures within all of the ICs in this amplifier. It compensates for the entire amplifier rather than just this IC. Now, in this case, L733 and L734 form the T-coil because pins 10 and 11 are tied together within the IC. In this case, we're using discrete components. And C733 right across the T-coil in the conventional manner. R735 is a bit inductive at these frequencies and compensated by means of the RC network, R734 and C734. Now, the output amplifier, U745, is essentially the same as U685 with the addition of a discrete pair of output transistors. The collectors are tied directly to pins 2 and 8, so the collector load resistor is also the reverse termination resistance for the CRT. CRT uses distributed deflection. R782A and B are two halves of a thick film resistor, and each of those resistors has a value of 187.5 ohms. Now, those resistors are a little bit capacitive, so the LR network, LR780, and the network on the other side compensates for that. Notice the resistors return to plus 50 volts down below. C783, just below the resistors there, bypass any common mode change that might occur to keep this thing from oscillating. We're talking about the entire amplifier now. All right, let's go back to that IC. It has a gain of about 15, includes an FT doubler. Now, the selected resistors right off pins 1 and 12, 6 and 7, shunt the 21.8 ohm resistors to a value of about 19.5 ohms. And again, there's a coding on the IC that tell the assemblers what value of selected resistor to use. In each case, we're trimming those nichrome resistors. Now, with an FT doubler stage, any compensation that appears between pins 1 and 12 is electrically in parallel with the compensation between pin 6 and 7. So we don't need to match compensations on either side. Now, the bottom network, composed of R747, C745, R749, C747, and then the same network over on the other side there, provide thermal compensation for the IC. Then the two top networks, and you notice that R743 and R758 are adjustable, provide some of the relatively low frequency compensation necessary for the delay line. Now, that leaves R745, C743, R760, and C758, and that network serves two purposes: some thermal compensation and some lower frequency delay line compensation. Standing current out at pins 8 and pin 2 is 83 mils per side. Now that current is reduced when we push the beam finder. You notice that the emitter tail off U745 comes down through R770 and to ground through the beam finder switch. However, when you push the beam finder switch, then R771 is inserted in the circuit, reducing the current and thereby reducing the scan. Just to the left of the beam finder is a circuit composed of Q776 and Q773, which is driven by the vertical off command, which overrides the beam finder action whenever we're writing a character. Now, vertical off command comes off to the left in at the base of Q776. It lifts the base and emitter of that transistor, lifting the base of Q773, saturating that transistor, and pulling the bottom of R770 down to ground, just like in the condition when beam finder is not pushed. Now, there's no such override in the horizontal amplifier, so when you push the beam finder button, the knob readout doesn't move vertically, but compresses horizontally. Pins 1, 12, 6, and 7 of the IC just above also look into transmission lines. The transmission lines are terminated in 100 ohms down below. However, we can't terminate that impedance right at those IC pins. So the transmission line on the IC is tapered, wide at the top, narrow at the bottom, such that the bottom is 100 ohms of characteristic impedance, and the top there at pins 1, 12, and so on is quite a bit lower. Couldn't find out how much. But it does present a resistive load to the emitters of the transistors inside of the IC. Now notice at the bottom of the page we have the, various supplies. There's 6, 6.9 volts, 5, 9, 12, and so on. Now we can use just resistive dividers in order to supply these voltages because typically these ICs present a rather constant current load. Now there's current switching certainly in the MO71 vertical channel switch. However, the current is shifted from one side of the amplifier to another, but the load on the supply remains constant. Now these voltage runs are rather long, and there's some noise on the supplies. So the lines are transmission lines. That is, we have a ground plane on one side of the printed circuit board and the run on the other, providing a characteristic impedance of 100 ohms, which is reverse terminated in the 100 ohm resistors and the half microhenry inductor across them. And then notice that the far side of this network is grounded from an AC standpoint with capacitors C794 and the rest of the capacitors in that network. A similar termination to the transmission line, which feeds the trace separation and character readout information up into the emitters of U685. Let's turn next to pull-out schematic 7, the horizontal amplifier. There are two horizontal amplifier schematics. We'll use the newer one from serial number 80,000 and up. CRT deflection sensitivity is 7 volts peak to peak per division, plus or minus 10%. Center screen voltage is 60 volts. And we'll limit in the positive excursion at 120 volts and in the negative excursion at plus 10 volts. Off to the left we have the inputs from the channel A horizontal amplifier and the channel B horizontal amplifier. The signal level there is 25 millivolts per division per side. On command from the display B command waveform in at pin 4, we select either channel A or channel B horizontal,